All right, hi Jennifer. So here's your problem that you asked me about. Okay, so we have a teeter-totter. Um, we have a fulcrum, and this represents the ground. And we have a one person who's 80 pounds on the left-hand side, which I'm guessing is a child, and that person is 6 feet from the pivot point of the fulcrum. And on the other side, we have a 100-pound child, and the distance from the child to the fulcrum is unknown because we want to know what distance will make it so these two children will stay perfectly level on this fulcrum, which means that they're balanced. Um, had the problem asked for them to be like this, where the teeter totter is at an angle, it'd be a lot more difficult. In general, of a beginning mechanics class or any type of problem like this, they usually want a fulcrum or a platform that is perfectly level. And the reason for that is it makes it a lot easier to do the calculations. So the first step is to draw a free body diagram. So let's go back to here. The free body diagram is the idea that we're only going to look at what's important here on the problem. So we're going to cut this platform away from everything that's unimportant. So the fulcrum point we'll just represent with an arrow, and then we'll represent the kids with dots. We won't worry about the ground because that's not acting on this platform. And we'll draw on the distances. So I'm going to go ahead and give you a sheet of paper. So we got our platform. Alright, and then if we don't know this distance, I'm going to do a little cutout showing that we don't know that. We got a force. Let's just call this FF. And then we have a child here. And we have a child here. And this child on the left is 80 lb, 80 pounds. The child on the right is 100 lb, 100 pounds. We have a distance. On this side, this distance is 6 feet. And this distance is X feet. Alright? Because we don't know what it is. This fulcrum is going to carry the weight of both children, so this is going to be equal to 80 plus 100 pounds or 180 pounds. But we really don't need to worry about this. This just represents our fulcrum. So with these problems, torque, this is actually a torque problem. We want the torque on the left side, which is acting like this, it makes it want to spin that way, is going to be canceled by the torque going this way on the right hand side. So if we add those together, it's equal to 0. Or we can think of it as the torques are equal in magnitude but opposite in sense. You'll hear it say describe the direction as a sense. So the one on the left is going to act counterclockwise, and the one on the right is going to act clockwise. And their senses might be in opposite directions, but their magnitudes will be the same. We should draw a little coordinate system so we know which is which. In this case, it's not going to be all that important. So we were talking about these forces. This would be in the y direction, y direction. This would be the y direction. There's no x direction forces. And also torque is calculated most easily by, instead of using a cross product, is to have items, the force is perpendicular to the path. Cross product can be written as the force times the path times the angle between the two, times the sine of the angle between the two. And if and only if, that's what this notation means, theta equals 90 degrees, then the sine of theta is going to equal 1. And so since our force and our path are perpendicular to each other, we don't need to worry about this sign. So I'm going to keep this on up. We're going to go ahead and calculate it. So if you remember back to here, we're saying that the torques, the sum of the torques, so the left-hand torque and the right-hand torque is going to equal to 0, right? This torque can also be called a moment. There's in terminology a little different with engineering, but for this case we're just going to use them interchangeably, and we'll call the moment, we'll call this a moment on the left, and this is a moment on the right. So I learned to always be very clear on how we draw these diagrams. So we're going to say a moment going in the counterclockwise direction. So this is counterclockwise direction is positive. Therefore, this side's going to be positive, this side's going to be negative. Right? And so we'll use m to represent the moment. So we'll say the sum of the moments should be equal to 0. Right? I recommend that you follow these steps. So the moment on the left-hand side is 80 pounds times 6 feet, and that's going to be, because it's counterclockwise, positive. And we're going to add this to the moment on the right hand side, which is 100 pounds times x feet, and its sense is going to be negative since it's acting clockwise, acting in this direction. So I'll put a big old minus sign so we know that's a minus, right? Always be careful because it's very easy to get your minus signs mixed up. And this is going to all equal to 0. I could have easily put this on the right hand side since I know this is equal, but in longer problems it's much better to do this all out and have it equal to 0, especially if you have more than one variable. So the left hand is 6 times 8, which is 48. So 480 pound-feet for the left-hand side, minus 100x pound-feet. It's equal to 0. Or we can say, I'm going to do a little hand waving and skip some steps here for the algebra. 100x pound-feet is equal to 480 pound-feet, right? And this is just a simple algebra problem. So 480 divided by 100. So let's go ahead and do that. X equals, let's double check. 4.8. I actually did it in my head, but I just wanted to make sure I was correct. And this is feet. So we're divided both sides by 100 pounds, but not by feet, right? So the pounds would cancel out, and we have the pounds would cancel out, so we have 4.8 feet. So our final problem, since we just discovered it, is this side's 6 feet, and this side is obviously not drawn to scale, 4.8 feet, 80 pounds, 100 pounds. All right. If you have any questions, just send me our email. Okay, bye.